Hello, welcome to video 8 in Advanced Mathematic Modeling. In the last video I gave you some examples of simple distributions of random numbers, and before I start to characterize distributions, I want to give you an example of distributions that are not so trivial to it's not so trivial where they come from, and so this Benford distribution is a very cool example for this. So what is Benford's distribution dealing with? So let's take a data set. Data set of numbers. So where could we get such a data set? For example, it could be a table of logarithms. So you think, why table of logarithms? But when you think, before we had our small calculators and computers, and if you needed to have a log of a number, most scientists or engineers, they had a book which had a table, and so it was just calculated once and written in a book, and so you just looked in this table to see what's the logarithm of a number. So that's at least at former times was very natural idea. If you want to have a table of numbers, a data set of numbers, just take your book of logarithms. But you could also have a table of inhabitants, of cities. So we have a data set which has all German cities, and it has the inhabitants or the city size. Or you could have a company, and you could have how is it called? You could have the numbers in the bookkeeping. In German Buchhaltung, or it's called accounting. So we just make a data set, a table of all the numbers that appear somewhere in the bookkeeping of this company. And you can easily consider other such data sets of large numbers, or large data sets of numbers. And now you could think, what can all of these data set numbers in all of these data sets have together? And now we make an experiment. For every number, we take the digital representation . Of a number. So for example, we have here the first random number in our table, and 1, and this is maybe 3,100, 350,000, whatever. Yeah. And now we take the first digit of this number, which would be the 3. So look at the first . So in this case, this would be the 3. And this is now our random number. And this we can do for all numbers in the data set. And then we get a distribution. So we call this maybe here our first random number. Then we take the second number in the data set, take the first digit, it's our second random number. And so we obtain a distribution. It's a discrete distribution because our digit can only be 1, 6, 7, 8, 9. Yeah. The first digit obviously can never be 0, so we have a distribution which is between 1 and 9. And that's our distribution p of x. And now the question, how does the distribution of these first digits of random numbers look like? So maybe the first idea is, since we don't know anything about these numbers, we would assume maybe it's a uniform distribution. But now I make a bet. I say, so we now make two complementary events. The first event is that this digit x is element of 1, 2, 3, 4. So this means the first digit is between these first 4 numbers, or the digit is in the last 5, 6, 7, 8, 9. So here it's 4 possibilities, here we have 5 possibilities. And now I ask you, do you want to play this game with me? We take this random city, look for the inhabitants, take the first digit here in the decimal representation, and if it's between 1 and 4, I get a coin from you, €1, and if it's between 5 and 9, I give you €1. Would you make this bet with me, and we repeat this 1,000 times? And now the question if this bet is who's winning will depend how this distribution looks like. And in fact, you would lose against me if you would do this, because smaller digits appear with much higher likelihood than larger digits. So if you do this quite often, you take such large data set, and then, for example, this p of 1 is about 30%, and then we give you 0.70%, and we go down to 12, 9, 7, and then always smaller numbers. And so here I've written down these probabilities that you can well compute if you just take such a data set and just run these experiments quite often. So we have a distribution which is decaying here, and so it's definitely not uniform, and it's really interesting that this distribution is kind of universal and largely independent what kind of data set you take. And now let's see who would win this bet here. For this, it's interesting to plot our cumulative distribution. So let's do this. Again, here we have x, and we have 1,